Birthplace of the Enlightenment and one of the most important cultural, artistic, and intellectual epicenters in history, Paris, in the summer that welcomed a new century, became a pilgrimage site for those who spoke the language of the universe. The capital of France hosted the Second International Congress of Mathematics, the most important assembly of the science that, by deciphering the universal language of nature, the language that weaves the invisible fabric of reality, reveals the harmony of what surrounds us, the hidden balance behind each number, and the ordered echoes of the cosmos. The 250 most relevant figures of the community were invited to a congress whose aim was to discuss and recognize the most significant advances in the field of mathematics at the dawn of the 20th century, as well as to promote international collaboration, the exchange of ideas among mathematicians from different countries to chart the course of what they hoped would be a new golden age for science. The presentations aroused great expectation, but if the Congress is remembered as one of the best in history, it is because of the presentation made by a young German mathematician, considered by all as the Great Promise. David Hilbert, in his lecture, exposed what he considered to be the most important unsolved problems. He wanted to establish a list of pending issues that, as mathematicians, they should solve because after decades and even centuries, no one had given them an answer. David had just presented what would later be baptized as Hilbert's 23 problems. The mathematician's lecture had an immediate impact. All the unsolved problems represented stimulating challenges for the listeners. But from the outset, all eyes focused on one of them. One that, not by chance, topped the list. One revolved around the most enigmatic concept of mathematics. An idea, subject of reflection and debate since the times of ancient philosophy, about eternity. A concept that transports us to the endless, to that which has no end. Hilbert's first problem was focused on describing the true nature of infinity, a concept that since time immemorial has fascinated and frightened us. An idea that dancing between mathematics and philosophy, on the faint border between reality and the world that exists only in our mind, has led us to explore a place where no path ends.
La idea de lo eterno, de un tiempo que nunca termina, o un pozo sin fondo. En cierto sentido, el concepto del infinito es algo tan antiguo como la propia humanidad. Una consecuencia de algo tan natural como contar y ver que siempre puedes añadir uno más porque los números nunca terminan. Porque cualquier número comparado con él es absolutamente insignificante. Esa es la idea básica del infinito.
Since the dawn of time, humans have fantasized about the idea of eternity. And we have evidence that this concept, which we would later call infinity, was a powerful inspiration for the great thinkers who laid the foundations of knowledge. The first historical record can be found in the teachings of Anaximander, a pre-Socratic philosopher from ancient Greece, who in the 6th century BCE spoke of something he called apeiron, an indeterminate matter, which is the beginning and the end of everything, from which the cosmos is born, develops and perishes. Anaximander believed that the constitutive principle of all things was not water, earth, fire, or air. Everything began and ended with that apeiron, without a concrete form, immortal, indestructible, ungenerated, and imperishable. A term that in its etymological sense means something indefinite, indeterminate, without end. The first approach to the concept of infinity. The infinitus, which means without limits or endless, had been born. Infinity had been baptized. In its purest conception, the philosopher believed that infinity was the fundamental principle of reality, an idea that generated profound rejection in his contemporaries and future Greek thinkers. Decades later, in the 5th century BCE, the philosopher Zeno of Elea became the first thinker to develop verifiable accounts of mathematical infinity. In an attempt to demonstrate that it was impossible to introduce these infinities into the real world without falling into paradoxes, To demonstrate the impossibility of real infinities, Zeno presented a thought experiment in which he himself was the protagonist. In his theorization, he imagines himself walking towards some trees. To reach them, he must first cover half the distance, something that takes a finite amount of time. Once there, he must walk half the remaining distance, something that again takes a finite amount of time. This process repeats over and over again, doing the same thing forever, dividing the remaining distance into smaller and smaller pieces, each of which takes a certain amount of time to traverse. If that infinity existed, if something could truly extend into eternity, and there could be endless fragments on the path, he would never reach the trees. The time required for this, according to the paradox, would be infinite. They had arrived at a paradox. Infinities made the most elementary foundations of human experience collapse. Later, in the 4th century BCE, Aristotle reinforced this rejection of the idea of infinity. The considered father of Western philosophy asserted that with it, physics collapsed. That if we wanted to do science, we had to rid ourselves of something that played with eternity in a childish way. Aristotle wanted to erase infinities from the physical world. There were no real infinities, only what he defined as potential infinities. Something you can aspire to but never reach. You can count as much as you want towards that infinity, but sooner or later the finitude of time will stop you. Although the concept of infinity may exist in our minds, everything, absolutely everything in the world is by nature finite. A judgment that deeply penetrated Western thought, and that would define our relationship with infinity for many centuries. We had to separate the abstract world of mathematics, where that infinity could exist, from the real world of physics, where everything has a beginning and an end, and where there is no room for eternity. But we were barely aware of the power that infinity had over knowledge. It was not until the 17th century that infinity began to be used more systematically and usefully in mathematics. Great figures, including Isaac Newton, laid the foundations of calculus, using infinitesimal concepts and limits to solve problems in geometry, physics, and engineering. Infinity was essential for the development of differential and integral calculus, a fundamental pillar in the progress of the sciences. Without it, descriptions of the world around us would be impossible. Although it was a concept rather than a number per se and did not follow the same rules as them, it was at our disposal to describe nature. Something that had arisen as a natural fear of the eternal had just opened the doors to a new era of knowledge.
El infinito se había convertido en una herramienta esencial para la ciencia. No debíamos entender ni mucho menos visualizar esa eternidad para usarla. Y aunque de algún modo lo habíamos domesticado, hubo alguien que quiso sumergirse en él, descifrar su naturaleza, mirar al infinito a los ojos, para revelar qué secretos se esconden en la eternidad.
In a time when we still didn't understand the concept of infinity, when we only saw it as a tool that gave cohesion to the language of the universe, a mathematician wanted to comprehend its true meaning. We were holding eternity in our hands, but had not given it a mathematical dimension. The Russian mathematician Georg Cantor was convinced that the notion of infinity was perfectly understandable if we looked at it from the most natural and innocent perspective. Like a simple children's game, Cantor set out to count infinities. He had founded a branch of mathematical logic that studies the properties and relationships of sets, which in their purest nature are abstract collections of elements that function as mathematical objects. For example, all even numbers can be grouped as a set, which is the collection of those numbers. By uniting the elements into these sets, using the tools of logic, you can perform simple mathematical operations that allow you to study the elements you have joined in them. He trusted that the so-called set theory was the key to bringing eternity to a place where infinity ceases to be incomprehensible. Cantor wanted to compare sets of infinities. The natural numbers 1, 2, 3, 4, 5, and so on to eternity are elements that can be encompassed in one of his sets, an infinite set. But the even numbers 2, 4, 6, 8 also extend to eternity. Technically, they are an equally infinite set. Still, logic tells us that compared to the natural numbers, the evens represent only half of them. Cantor wanted to know if this also applied to their infinite sets. Essentially, the mathematician wanted to decipher something that at that moment seemed absurd. Determine if there are infinities larger than others. And his set theory opened that door for him, because he didn't need to count up to that infinity. All he had to do was compare the sets of infinities and look for a one-to-one correspondence. If he found a way to match them up, that meant both infinities were the same size. If there was no way to find that perfect match, he could demonstrate that indeed there are different degrees of infinity.
Si encuentras una forma de hacer parejas, puedes decir que dos conjuntos tienen el mismo tamaño, porque pensemos qué quiere decir que dos cosas sean iguales. Cuando digo que tengo el mismo número de dedos en la mano derecha que en la izquierda, ¿qué es lo que realmente estoy diciendo? Obviamente puedo contar 5 y 5, pero hay algo más elemental que puedo hacer, y es emparejarlos. Todos tienen una correspondencia 1 a 1. No necesitas contar para ver que hay el mismo número de dedos. Y este principio aplicado a un lugar donde no puedes contar porque nunca llegarías al final, es lo que daba esperanzas al matemático.
In 1873, Cantor began his journey into the realm of infinity by comparing those two sets, the set of natural numbers and the set of even numbers. Intuition tells us that the infinity of naturals should be larger than that of evens, since after all the evens are only half of all numbers. But logic failed when eternity came into play. Simply by doubling the set of naturals, transforming them into evens, there was a perfect correspondence between the two sets. You can pair them up, and therefore you don't need to count to see that they are the same size. Both infinities are equally large. Cantor called these infinities with a one-to-one correspondence countable sets. It doesn't matter that in our finite minds we believe that real numbers are fewer than the set of all numbers. He had shown that both infinities are equal. In eternity, there are exactly the same number of even and natural numbers. With that first phase resolved, Cantor moved on to the second. In this case, he was going to compare the infinity of natural numbers with the infinity of integers, which includes all positive and negative numbers. Once again, intuition tells us that the infinity of integers should be larger double in fact, because it includes an eternity of negative numbers that are not included in naturals. However, simply assign 2 to -1 of the integers, and start a correspondence where all negatives are even and all positives are odd. A perfect match has been achieved again. Once again, he had shown that both infinities, despite our logic pushing us to believe otherwise, are exactly the same size. At that moment, Cantor went a step further, pushing the complexity of the experiment to the limit by replicating the procedure with fractions, with rational numbers. Between any two integers there are infinite fractions, so their infinity would have to be larger. But once again, logic failed us. Cantor created a table where he took a series of fractions where the numerator represented the row and the denominator represented the column. It quickly became clear that if he started counting in a line, he would never reach the second row, as he wouldn't even reach the end of the first. Therefore, to look for that possible correspondence, he had to count in a different way. If he took the diagonals, if he started at the top left and swept forward and backward diagonally, he was creating a list of all the fractions. In other words, he had found that one-to-one correspondence between fractions and natural numbers, which in that matching were the step of each jump. Again, counterintuitively, both infinities were equally large. He had only one challenge left. But it was precisely at that moment that everything took a strange turn.
Habiendo estudiado los naturales, los enteros y los racionales, solo faltaba un grupo para completar el mundo de los números reales, porque no todos los números pueden representarse como fracciones. El número pi, el número e o las raíces cuadradas de 2 o de 5 son ejemplos de números irracionales, números cuya expresión decimal no es exacta. Sus decimales se extienden hasta el infinito y no se repiten de ninguna forma periódica. Los irracionales representaban el último y mayor reto para Cantor.
Let's suppose we have made a list of all the decimals that exist. It's impossible, but let's pretend we have. Such a list would extend infinitely both downwards on the page and to the right, as there are infinite irrational numbers, and each of them has an infinite number of non-repeating decimals. In our limited list, let's create random irrationals, and when finished, let's create a number by taking their diagonals. The first decimal from the first row, the second decimal from the second row, the third decimal from the third row, and so on until what would be virtually infinity. Starting from this number closely linked to the original irrationals, we're going to write a new one with a simple condition. If in the base number we have a 1, we're going to change it to a 2. If there is any other number, we're going to change it to 1. Inevitably, by doing this, the new number will not appear in the original list of irrationals. It is completely different from any other. It's not the first number because it's different in the first position. It's not the second because it's different in the second. It's not the third because it's different in the third. And so on to infinity. No matter how much you search, it will be different in at least one character, the diagonal digit. We've created a number that is not in the list. Therefore, what we learn from this is that you can't enumerate all decimals. Unlike the previous ones, you can't count them. We're facing what Cantor had just described as an uncountable set. He had just stumbled upon a new type of infinity. There were more real numbers than naturals because when irrationals came into play, we were unable to find a one-to-one correspondence. Pairing was impossible because the infinity of reals was larger than that of naturals. Cantor had just demonstrated that not all infinities were equal, that there were eternities more eternal than others. A revolutionary conclusion that shook the foundations of the mathematical community generally negatively. Many believed it was nonsense and tried to ridicule his research. However, he continued to explore that realm and wondered if between those two infinities of different sizes he had discovered there were infinite infinities. If there was a gap between them, which was what he believed, or on the contrary, there was a continuity of eternities. Thus, in 1878, Cantor formulated what became known as the continuum hypothesis, a conjecture in which he asserted that there are no infinite sets whose size is between the set of real numbers and the naturals. But he couldn't prove it. Over time, his ideas became increasingly accepted, symbolically closing his arc at that Paris Congress in the year 1900. Because when David Hilbert gave his lecture about the 23 great unsolved problems, the first of them was precisely Cantor's continuum hypothesis, which finally received the recognition it deserved. The world embraced the findings, and we understood that infinity was much more than a tool for calculations. In that eternity, there was something much deeper that still awaited deciphering.
Cantor nos había regalado una de las más elegantes revelaciones de la historia de las matemáticas. El infinito ya designaba algo eterno, algo sin un final, y sin embargo, había demostrado que hay infinitos más grandes que otros. Y para demostrar estas extrañas propiedades, para exhibir cómo nuestras finitas mentes son incapaces de abarcar la infinitud, David Hilbert nos invitó a un lugar en el que jugar con esa eternidad.
With the aim of fostering public interest and engagement in infinity, with the continuum hypothesis still unresolved 2 decades after the Paris Congress, in 1925, David Hilbert devised one of the most famous thought experiments in history. The mathematician invited us to visit the magical Hotel Hilbert, a very special hotel with a unique feature. It has an infinite number of rooms that night, for the first time since its opening, have achieved full occupancy. An infinite number of guests have filled the infinite rooms of Hilbert's hotel. Later, a person arrives at the hotel reception requesting a room for the night. Technically, the hotel is full. But the director knows that in his hotel there is always room for more people. However, a dilemma presents itself to him. Considering that there are infinite rooms, the logical thing would be to tell the guest to stay in the room at the end of the hallway, towards infinity. The problem is that there is no end of the hallway. There is no last room. You can't send him to infinity because he will never reach it. You have to give him a room number, but all the infinite rooms are occupied. Luckily, the director comes up with a solution. He knows he can't start from the end because there is no end. If he can't send the guest to infinity and he needs a specific room number, it suffices to instruct the infinite guests already in their rooms to gather their belongings and move one room. The person in room 1 goes to room 2, the person in room 2 goes to room 3, and so on to infinity. Assigned to room n+1, everyone in the hotel knows their room number, and the first room has become vacant for the new guest. Thinking he has overcome what could have been the worst night of his life, a few hours later, the director faces a much bigger challenge. Infinitely bigger, in fact. Suddenly, an infinite bus with an infinite number of passengers parks in front of the hotel. They all want a room. They must accommodate an infinite number of guests in a hotel already full with an infinite number of complete rooms. His initial strategy doesn't work. He can't ask the old guests to move infinite rooms to the end of the hallway, because they would never find that place. Luckily, the clever director finds a way to free up infinite rooms by asking the guests to move a finite distance. Through the loudspeaker, he announces that everyone must check their room number, multiply it by 2, and go to the room whose number is the result. Thus, the person in room 1 goes to room 2, the person in room 2 goes to room 4, the person in room 5 goes to room 10, the person in room 23 goes to room 46, and so on to infinity. Although for those further down the hallway, it represents a huge journey. The director has instructed everyone to go from room n to room 2n. Everyone has doubled their room number, meaning all the old guests are in an even-numbered room. All the odd-numbered rooms, an equally infinite set, are now vacant. But even then, it seems that life hasn't finished hitting him. Because after finishing placing those infinite guests, infinite buses suddenly park in front of the hotel, each with an infinite number of passengers. And of course, he must find them rooms because his policy is clear. No one is left without a place in the infinite hotel. To achieve what seems like an even more impossible mission than the first ones, the director assigns all guests a new room number that is 2, the first prime number, raised to the power of the current room number. Therefore, the guest in room 9 has to go to the room resulting from 2 raised to the 9th power, which is 512. Having rearranged the guests, it's time to find a place for the passengers, and the orders are clear. With all the infinite buses numbered, passengers on bus number 1 are told to go to the room resulting from raising 3, the second prime number, to the power of their seat number on the bus. Therefore, the passenger in seat 9 has to go to the room resulting from 3 raised to the 9th power, which is 19,683. Passengers on the second bus are assigned powers for the next prime number, 5. Those on the third bus, the next one, which is 7. Those on the fourth, the next one, which is 11. And so on to infinity, filling the hotel perfectly with infinitely new guests. Since all these numbers have only 1 and the powers of prime numbers from their base as divisors, there are no overlapping room numbers. The infinite passengers from the infinite buses have found their accommodations. The doors of Hilbert's infinite hotel remain open.
Aunque el hotel de Hilbert ya sea una pesadilla logística, estamos explorando solo el nivel más bajo del infinito. Si en los infinitos buses los pasajeros no estuvieran en asientos numerados y estuvieran mezclados al azar sin seguir ningún orden, no podríamos encontrarles un sitio, porque entonces los buses estarían comportando como números irracionales. Un infinito que, como Cantor demostró, es más grande que el infinito de los enteros y, por tanto, más grande que el hotel de Hilbert.
The moral of the parable of the hotel is that infinity does not behave like anything comparable in our human experience. Our intuition and logic collapse when entering it. A hotel where there is always room for infinite people even when it is full. Hilbert's tale was just a demonstration of the surprising properties that Cantor showed, and how difficult it is for our minds to conceive a concept like infinity. But at the same time, with the growing popularity of the tale, having already understood its mathematical depth, there remained one final frontier. To resolve the doubt that since the times of ancient Greece had obsessed all those who had observed eternity. To determine if infinity exists in our world.
En lo que respecta a las matemáticas, no hay duda de que el infinito existe. Si existir es poder operar con él y analizar sus propiedades, ahí tiene su certificado de existencia. Pero que lo haga en el mundo físico es algo muy distinto. Aplicado a nuestra realidad, el infinito siempre nos conducía a paradojas, a lugares donde los cimientos de la ciencia colapsaban. Pero tras mucho tiempo de negar su existencia, los ecos del infinito empezaron a sonar desde la oscuridad, a través de unos monstruos que esconden el lugar donde todos los caminos terminan.
In its intrinsic elegance, Einstein's equations hit a new conception of the universe. The theory of general relativity, since its publication in 1915, connected the mathematical world with the physical, forever transforming the view of space and time. But initially, neither he nor anyone else was aware of the dark secret lurking among its formulas. The mathematics predicted the possibility that after the death of a massive star, the fabric of space-time would collapse into an infinitely small region. The architecture of the cosmos fractured at a point. The birthplace of an invisible monster with the power to drain light and stop time. Pushed to the limit, the equations of general relativity predicted the existence of what were baptized as black holes. Beasts whose hearts hit a singularity where the laws governing the behavior of the universe collapse. Where mathematics collapse prey to an infinite well. The singularity of black holes was an eternal curvature of space-time. A place where all the mass of what was once a star is condensed into a place that is the absence of itself. An infinite density that causes the entity to behave like a dark pit in the universe. Everything is drawn by the gravitational power of the singularity. Faster and faster, like a river accelerating in its course. At every moment, escaping the current becomes more difficult. until a point is reached where no matter how fast you swim, a cascade has formed in space and time. A point of no return, the event horizon. A place around the singularity from which even light cannot escape. The border between the universe we know and that hidden in the unknown and dark depths of a black hole. A monster that guards within its bowels what seem to be infinity. And although everything seemed too strange to be true, that no theory leading us to infinity could describe reality, in the spring of 1971, we came across the first sign of the existence of something eternal in nature. Years earlier, astronomers had detected a strange source of X-rays 6,000 light-years away, which they named Cygnus X1. The emission of radiation seemed to come from a massive star orbiting around something invisible, hidden in the darkness of space and time. Conjectures about what could be a black hole, until then considered mere mathematical curiosities emerging from playing with Einstein's equations. Spread throughout the astrophysical community, the echoes of monsters and infinity were sounding for the first time. And finally, all those intuitions materialized. Measurements made on the star in the Cygnus X1 system showed that it was orbiting around the invisible object at such a high speed that any known celestial body was ruled out. Only one option remained. It had to be a black hole. A guardian of darkness that by devouring a blue supergiant star was creating the so bright source of radiation. They had always been hidden under the shadow of their own darkness, but we had found them. Black holes were a reality, and that infinity they hid in their hearts. A disturbing revelation. The infinite curvature of the singularity, the infinite density that causes everything that falls into its depths to be lost in a place where physics stops and time loses its meaning. Never before had we had infinity so close, but everything pointed to the fact that in the monsters was hidden what for so long we had considered something that only inhabited our imagination.
Más tarde entendimos que el infinito predicho por las ecuaciones, más que una realidad, es una advertencia de que algo en nuestras teorías falla. En el corazón de un agujero negro las matemáticas de la relatividad colapsan, y los efectos cuánticos de la gravedad reinan. Necesitamos una teoría de la gravedad cuántica que describa algo muy pequeño pero con mucha masa al mismo tiempo. Algo que la física actual es incapaz de hacer.
Until we have it, that infinity will continue to appear to remind us that there is still a long path to travel. But at the same time, to tell us that our ambition to find a palpable eternity, with a true infinity that exists beyond our minds, does not have to be in vain. Infinity had pointed us the way. There were indications that eternity in space and time could inhabit the world beyond mathematics. It was time to explore our place in the universe and venture into the true realm of infinity. After a 4-year mission in March 2013, the Planck telescope offered the most complete and detailed image of the cosmic microwave background. An ancient radiation that permeates the entire observable universe and originates from the instant when 380,000 years after the Big Bang, the first photons were released from the opaque plasma ball that was the primordial cosmos. There is nothing farther in space or time that we are capable of seeing. Planck would have gifted us an image that captured the ephemeral radiation, those ashes from the birth of the universe, originating from the moment when light was born. The cosmic microwave background, in quality never before achieved, was revealing a lot of information, allowing us to estimate the age, expansion, and constitution of the cosmos very precisely. But above all, we were observing the beginning of everything. That image was the frontier. For the first time, we had reached the limits of the universe. what lay beyond was something beyond the end of the world. The cosmic microwave background represented the edge of our observable universe. The visible part of the cosmos has a diameter of 93 billion light-years and contains around 200 billion galaxies, each of them with hundreds of billions of stars. Beyond that observable universe, there is no way for us to observe anything. As light has not had time to reach us, and given the accelerated expansion of the cosmos, it is something that will forever be beyond our reach.
Podemos pensar en el universo observable como una esfera con un centro focalizado en ti mismo. Mires donde mires, ese cosmos se extiende 46.000 millones de años luz en cada dirección. Si te mueves, tu universo observable se mueve contigo. Por tanto, es cierto que existe una frontera en el universo, una frontera en el tiempo. Miramos hacia el pasado hasta que básicamente no hay más pasado que mirar. Pero aquí nadie ha hablado de una frontera en el espacio.
Wondering what lies beyond the observable universe is as human as questioning what lies beyond the horizon of the ocean. And precisely for that reason, through those ashes of the birth of light, we were going to navigate a sea of darkness, and perhaps find infinity in the universe. To know the true scale of the cosmos, the only thing we can do is decipher its shape, the geometry of the universe, how it curves on the large scales, and there was only one thing that was going to give us the answer: the most ancestral light that still traverses the oceans of darkness. With the results of Planck in their hands, astronomers knew that light would travel in a straight line if the geometry of the universe was flat, and would describe an arc if space was curved. Those curvatures were going to be so subtle that we needed to look as far in space as we could. And this was where the cosmic microwave background came into play. This radiation is not completely uniform. It presents tiny temperature variations of the order of 100,000th of a degree in different regions of the sky. These deviations, known as anisotropies, were shown to exhibit a pattern of triangles formed from the interaction with the so-called baryon acoustic oscillations, primordial sound waves, that propagated through the primordial plasma of the early universe. Therefore, the shape and size of these triangles in the cosmic microwave background depend on the global geometry of the universe. So, using theoretical models and computational simulations to generate expected triangles for the different possible geometries of the cosmos, they could compare those predictions with the actual observations. And the result represented one of the highlights in the history of astronomy. Everything pointed to a flat geometry. There were no indications of any curvature, of any closed geometry. The cosmic microwave background was suggesting that probably the universe was flat on a large scale. There was a certain degree of uncertainty, as a very slight curvature that we are unable to perceive with current precision was possible.
En tal caso habría una geometría cerrada, con un universo esférico en el que nuestro universo observable representa una porción tan diminuta que no somos capaces de detectar esa curvatura. Pero sea como sea, ahora mismo toda la evidencia conduce a un universo plano. Y aunque no lo parezca, esa geometría tiene unas implicaciones muy profundas. Porque un universo plano es inevitablemente un universo infinito. Y con ello, estamos abriendo las puertas del multiverso.
With the discovery of the likely flat geometry of the universe, the astronomical community focused on understanding the implications of what they had just deciphered. A secret imprinted in the ashes of the Big Bang that had been waiting for 13.8 billion years for us to be able to read it. In that infinite space, there exists a region beyond which objects move away from the central observer at a speed greater than the speed of light due to the expansion of the universe. That sphere is what in cosmology is known as the Hubble volume. In our Hubble volume, there is a finite amount of energy carried by an also finite amount of particles. Everything that makes up our universe results from the combination of 10 to the power of 80 particles. Everything we are, Everything we see in the sky, everything is contained in that box, which in a certain sense is our Hubble volume. But in a flat universe, a cosmos that stretches throughout eternity, there must exist an infinite number of Hubble volumes, unable to interact with each other but sharing the same fabric. Disconnected but playing under the same physical laws. A multiverse governed by infinity. Flat geometry pushes us to conceive an infinite number of Hubble volumes, each of them with those 10 to the power of 80 particles, the pieces with which chance can play. An inconceivably large number of configurations that may feel like infinity in our minds. But nevertheless, it is insignificant compared to true infinity. You can come up with trillions and trillions and trillions of different ways to rearrange these particles. Each Hubble volume will have a unique configuration. Each universe will be special. But if space is flat, if it extends eternally, if the multiverse is inhabited by an infinite number of volumes, inevitably that pattern of particles will have to repeat. Given enough time, there will be one where the configuration repeats. One in which those 10 to the power of 80 particles restructure exactly the same way. If we have finite options to build a universe, but an infinite space, it is certain that there will be repetitions. It is estimated that Hubble volumes exactly like ours would be separated from each other by an average distance of 10 to the power of 10 to the power of 115 meters, a number that, to be written, would require a sheet larger than the observable universe itself. But that distance is still finite, insignificant compared to infinity. In fact, everything that can exist within that box will exist an infinite number of times, which means that there will be an infinite number of copies of ourselves. In another Hubble volume where the configuration of particles has been repeated, the entire history of our universe will be duplicated infinitely. Eternal copies of you, of me, and everything around us. Because in an infinite universe, everything that can happen will happen infinitely. Everything is happening in parallel to us, in the unreachable distances of an eternal ocean. A multiverse in which parallel realities are not only possible, they are inevitable. In other Hubble volumes, there would be infinite worlds where everything is happening exactly the same way, but also infinite ones where the course of history has been different. From the Nazis winning World War II to an Earth where 66 million years ago, no meteorite hit to end the age of dinosaurs. All these infinite realities happening simultaneously and for all eternity in a multiverse that germinates from the pure geometry of the cosmos. Something that guarantees that we will all live eternally. Because there will always be a place in that ocean where we continue to exist. There will always be a copy of ourselves out there. All those moments you would want to live over and over again will never disappear. They will continue to happen somewhere beyond the end of the world. Because everything and everyone is eternal in it.
Ese es el poder del infinito sobre lo finito. En las fronteras del espacio y del tiempo quizás hayamos encontrado ese verdadero infinito. Una idea que parecía habitar solo nuestra mente, una herramienta al servicio de las matemáticas, puede haber abierto las puertas de la eternidad. Pero sea cual sea la naturaleza elemental de la realidad, lo único que sabemos con certeza es que todo lo que importa en nuestra vida es finito.
Because even though our universe may now seem small, it is more than enough to find our purpose. It is infinitely large for us. And perhaps that is the true realm of infinity.